speaker of this session, which is Radu Roiban, who will tell us about from scattering amplitudes to gravitational waves observables.
Thanks. Let me try to share the screen, the right screen, that is. What do you see?
I can see your slide. Looks
the right slides, I hope.
I think so.
All right. So thank you very much for the invitation to speak here. So I was asked to review the recent developments connecting scattering amplitudes and gravitational waves in the context of the two-body problem. And this is exactly what I'm going to do. Once my computer lets me change slides. So we have lots of theoretical and experimental experience with the two-body problem in Newtonian mechanics. First of all, it's integrable, so one can say that once it's solved, there's nothing left to do, and that's probably true. We know that closed orbits are elliptical, there is no perihelion precession, everything reduces to the motion of a particle in the center of mass. There is an additional conserved quantity, the Laplace-Runge length vector, which is the origin of integrability in this problem. And it is also known that once we include relativistic effects, even specially relativistic effects, this Laplace-Runge length vector is no longer conserved. However, there exists a field theory generalization of this, and it goes by the name of the dual conformal symmetry. So one can hope that some strange integrability kind of structure might exist in a more general context in the two-body problem. The generally relativistic two-body problem is much more interesting and much more difficult. Of course, we know that there are departures from Kepler's results, which are basically the original confirmation of general relativity. And we also have lots of data showing that there are important relativistic effects. So here are several pictures taken from the LIGO catalog, and I will not dwell on them too much because the next two talks will provide a much more up-to-date information on what's going on at LIGO, and they can say a lot more than what I can possibly say. For the purpose of this talk, however, all we need from these pictures is here is a cartoon, which from all these pictures here is a cartoon which I stole from this paper. And from this cartoon, even we need a little bit less. We need to notice that the conservative dynamics of this binary motion, which is the thing that gives us the big wiggles in this plot, is separated in scale by the rate from the rate of radiation emission, which gives the rate of change of the frequency of these wiggles. So with this in mind, it makes sense to separate these two physically distinct quantities, the conservative dynamics and the radiation emission, and focus on one of them. In my case, I will focus on the conservative part, though I will also mention a little bit about radiation emission later on, because scattering amplitudes turn out to have some something to say about that as well. So focusing on conservative part, this is typically described by the post-Newtonian theory, which one can call a weak field and non-relativistic expansion. For closed orbits, this expansion is in the velocity and the ratio Newton's constant times the mass divided by the distance between the two companions. And both of them are of the same order, and they're much smaller than one. They're of the same order because of the Virial theorem. Another expansion which has become popular in the recent years is the post-Minkowskian expansion, which could be called weak field and relativistic. It is what a field theorist might call just perturbation theory, because it's an expansion in Newton's constant, and the velocity expansion from the post-Newtonian point of view is resummed. So one could imagine taking the velocities to be large, that is of order 1. And last but not least, there is the so-called self-force expansion, which is an expansion in small radii, in small mass ratios. And in this case, both the velocity and gm over r are of order 1. So this self-force expansion also resums bits of perturbation theory in Newton's constant. So what do we know about all of these is summarized in this plot. So this is some kind of Lagrangian that captures pretty much everything I said. And here are two formulae capturing the post-Newtonian expansion and the post-Minkowskian expansion. So everything here is fixed sum of exponents n and k minus n. So this is kth order in the post-Newtonian expansion, and this is kth order in the post-Minkowskian expansion. Clearly, these two overlap, and they overlap non-trivially. So here is how they do. Post-Newtonian expansion runs vertically, and post-Minkowskian one runs horizontally. So from a post-Newtonian point of view, the first term that has ever been known was Newton's term from 1687, and then the next correction to that is Einstein, and then it goes on. And the reason the fifth post-Newtonian order is circled but with a different color is that most of it is known. There are a couple of coefficients in these in here that are yet to be determined. There are two numbers, but those numbers are important. From a post-Minkowskian point of view, the first complete results, the first order in post-Minkowskian expansion was derived in the 1980s by these people here. And then the next order took quite a while. It was completed in 2018. And then the third order was computed shortly thereafter using amplitudes techniques, and this will be part of the focus of my talk. And then the order after that is, well, some part of it is complete, some part of it is not yet complete, which is the origin of the star. And this star will appear later on in various contexts and in different colors, and it always means the same thing. And I will be happy to explain exactly what the star means. I will say it on my own anyway. So this said, how do scattering amplitudes fit into this story? Well, they fit in several different ways. Perhaps the simplest way to say it is based on the observation that scattering and bound state dynamics are governed both by the same effective Hamiltonian obtained from, say, fundamental particles coupled with GR, from which you integrate out the gravitons. So with this in mind, one can consider finding a Hamiltonian by studying scattering amplitudes and then changing the boundary conditions, that is changing the energy to negative energy, and then study bound state dynamics. So the mantra here is you have to integrate out the gravitons. A second version in which scattering amplitudes feature in this problem is that they can serve, when properly interpreted, as a generating function for scattering observables. And with such a generating function in hand, one could imagine analytically continuing those observables to bound observables. So here's another star, and this one actually means something slightly different from the previous one. And it means to say that there are certain features of these Hamiltonians which are non-local, and for those, the effect of those non-local pieces of the Hamiltonian, this analytic continuation is yet to be sorted out. But in principle, a strategy of this type should work at some level. And yet another version in which scattering amplitudes fit into this is through the computation of final state scattering observables. Now, this is a mouthful, but it's something that is a variation on the theme of certain observables in collider physics known as event shapes, which colloquially could be called dressed cross-sections. So the idea is that you compute a cross-section, and instead of just asking what is the probability for particles to go whichever way with some energies, you measure something in the final state. In this case, it would be this O. And it is basically what you get is basically the expectation value of that one observable in the final state. So an actual formula that holds both classically and quantum mechanically is the first one, and pictorially is the second line. So this is the dashed line here is basically the integration over the final state in the cross section, and there you measure this O. Since we're talking here about scattering, clearly this is again something of a like a scattering observable. So to get bound state observables, one has to analytically continue, and the star means exactly the same as before. So here, these are the three ways in which currently scattering amplitudes fit into the two-body problem and gravitational wave physics. So before I go on, are there any questions on this? All right. So why the post-Minkowskian expansion and not sticking with the post-Newtonian expansion? Well, first of all, if we have the post-Minkowskian expansion, we can always go back to the post-Newtonian one by just expanding in velocity. But having the full velocity dependence increases the reach of the post-Newtonian calculations. It also helps with modeling LIGO searches for transient events like, black holes that pass each other and actually scatter each other instead of being bound. And on a more fundamental level, the post-Minkowskian expansion allows us to explore the structure of perturbation theory. For example, it lets us probe whether there is a generalization of Laplace-Runge lens vector to GR. It also exposes unexpected functional dependencies. It may expose unexpected functional dependencies on structures. And it may expose structures in other contexts like spin-dependent observables. More generally, carrying out calculations in the most general way possible tends to reveal structures and patterns, which in turn leads to new calculational tools and to new questions, which in turn lead to more calculations. And this is a cycle that can go on forever until, well, you run out of steam or you run out of computer power for new calculations and so on. But it always tends to lead to progress. And, in the field of scattering amplitudes, this cycle led to high loop calculations in various theories of interest. So apart from this, the post-Minkowskian expansion is a complementary approach to the post-Newtonian one, and also to the scattering amplitudes approach in general is complementary to various techniques used for post-Newtonian calculations. Therefore, it can reveal new perspectives on gravitational interactions. And last but not least, having again a full velocity dependence can provide information for semi-analytic fits to and semi-numerical fits to fully numerical GR data. And finally, the reason to look at the post-Minkowskian calculation is that LIGO theorists asked us to do that. So here is a quote from an abstract of Thibaut Damour's paper from 2018, in which he is urging amplitude experts to use their novel techniques to compute a certain two-loop amplitude for scalars coupled to gravity. Why two loops will hopefully become clear in a little bit, but as it turns out, if one is interested in scattering, say, heavy objects like planets or black holes, the classical limit works a little bit differently from what we are taught in grad school. H bar to 0 is not forcing us to sit on tree-level amplitudes, but it picks out certain pieces of certain higher loop amplitudes. And this is why Thibaut was asking for this two-loop amplitude. And hopefully this will become clear in a little bit. So scattering amplitudes are the bread and butter of quantum field theory calculations. And the textbook approach, or at least the older textbook approach to them, makes use of Feynman diagrams. And as I'm sure everybody in this audience knows, they will eventually get excessively complex if one goes to sufficiently high loop order or sufficiently many external legs. Now, the novel methods Thibaut was talking about are listed here. They involve recursion relations, generalized unitarity, color kinematics duality, double copy, and there are certainly new integration methods. And all of these make calculations substantially easier and substantially more straightforward than using Feynman diagram calculations. The key that makes us, that lets them do this is that they maintain gauge invariance. As you know, Feynman diagrams involves a sum of terms, each of which is not gauge invariant, and consequently they contain a lot of garbage, which cancels at the very end if everything is done correctly. The power of these methods relies on the fact that every single bit that enters in calculations is manifestly gauge invariant. So all the garbage has already canceled out. So there is nothing to cancel out at the very end. So here are a few milestones that I was alluding to a little bit earlier. It involves certain 5-loop calculations and 4-loop calculations in very supersymmetric theories, and lower loops in less supersymmetric ones. Supersymmetry is, of course, not essential. The reason here people focused on these is for reasons specific to these particular theories considered. But of course, when supersymmetry is present, it does tend to make things quite a lot simpler, which is why people tend to like it. And also here I'm mentioning 4-point calculations, but of course there are scattering calculations of more than 4 particles, and they can also be computed with exactly the same methods. So as it turns out, the post-Minkowskian expansion certainly plays on amplitude strengths, if only because post-Minkowskian expansion requires resummation of the V expansion, and scattering amplitudes in relativistic quantum field theories are by construction relativistically invariant, so they naturally resum this. Like I said, we have great tools. We also have great effective field theory techniques to integrate out gravitons. We can model black holes when they are suitably large separated by point particles, even when they are spinning. And we can also include subsequently finite size effects, and also take care of all the spin dependence if necessary. So this said, where we are at, and I will list most of the results here and come back to them in a little bit and show you certain various expressions. So as I was saying, we computed the effective interaction potential between massive bodies at the 3rd and 4th order in Newton's constant. This star here means yet something different from before. It's the same as the first star. The radiation contributions to certain observables was computed at conservative radiation observables contribution was computed at order g³. Certain dissipative observables, like the energy and momentum loss, was also computed at the same order. Spin-dependent observables and were computed at this order. And also there is a conjectured all-order expression and all-order generating function for observables for spinning systems. And also leading finite size effects have been also computed to, and there is quite a bit of structure that has appeared there too. So here is some of, this is the Hamiltonian or the interaction potential to the order that's known at the moment. So this is the general structure of the Hamiltonian for some point particles that are relativistic. And it starts with Newton, dressed with some momentum dependence, and then corrections to that depend on, that go up to g⁴. So as I was saying, the first 2 orders were computed in 1980 and 2018. Our work amounts to finding this C3 coefficient, which by the standards of amplitudes is tiny. It's just this function. Doesn't have anything hidden apart from these definitions. And the 4th coefficient, C4, is a little bit more complicated, and it involves an iteration of terms that appeared at lower orders, these C1, C2, C3, and then it involves some functions which will appear on the next slide. So the thing that I'd like to draw your attention to is this 1/epsilon. So here epsilon is a dimensional regulator. So since it appears in the Hamiltonian, you can already tell that something is a little bit amiss, and this is the reason for the various stars that I was pointing out a little bit earlier. So anyway, these are the functions that were not written on the previous slides. They are a little bit longer. So now back to the star. So the star means that this Hamiltonian, as it stands, is incomplete. And the fact that it's incomplete, you can tell from the presence of the 1 over epsilon and the presence of this mu here, which is the dimensional regularization scale. In any physical quantity, both of these should go away. And their origin is quite well understood. They also appear in post-Newtonian calculations, which is why they are well understood. So physically, it has to do with emission of radiation from the binary, which scatters off the space-time, and it is reabsorbed by the binary itself. So it doesn't make it off to infinity. It's a conservative effect because, again, the graviton doesn't make it out to infinity. But it is also not a genuine potential because it does not come from the exchange of a graviton between the two bodies. So these have to be computed separately. And we have not computed them yet, but they're in the works. So, right. So now with these in hand, one can, of course, wonder whether what I was trying to sell you a little bit earlier holds water. That is, if these could potentially be useful for gravitational wave observations. And at least for the third order, for G to the third, which is complete, this was studied back in 2019, shortly after our paper appeared. And the thing to look here is at the teal line, or the turquoise line, which is numerical GR predictions for binding energy versus orbital frequency in a binary with equal mass ratio. And so this is the numerical GR predicts the turquoise line. And an effective one-body theory based on the third post-Minkowskian potential that I was showing you a little bit earlier is the dashed line right above it. So you can tell it does quite a bit better than various other PN models. So I guess what I was trying to sell you holds some water, though of course this is not completely conclusive because this modeling does not account for the emission of radiation. So they are encouraging, and these results are encouraging and motivate a more comprehensive study, but they are not, these pictures are not the last word on the topic. Now, even though the fourth order is not complete, one can ask whether how it fares compared to post-Newtonian effective one-body models and numerical GR. So to do that, this is taken from work in preparation by these guys. So to do this, one has to put in a little bit of physics and regarding what happens to the 1 over epsilon term. And of course, when everything is said and done and the missing pieces are added, this term has to cancel together with the scheme dependence. So what they did was just to drop these terms. And what they find is the dashed red line, which is pretty good given that things are missing. My apologies. The dashed red line is the fourth post-Newtonian effective one-body model, and the golden line is this Hamiltonian from which these terms have been dropped, and the black dashed line is numerical GR. So things are not totally off, and of course this is not totally conclusive because this is, like I said, not the entire answer, but it does give us motivation to complete the tail calculation. So this said, this concludes what I meant to say about interactions of spinless bodies. One can apply the same scattering amplitude technology to analyze spinning bodies. And I will not tell you, I will not show you the details of exactly how this is done, but the result of that study is a formula that looks like this. Here, O is any observable that you might desire. D is some strange operator, which looks like a half a Poisson bracket, and chi is a function that's extracted from scattering amplitudes this way. It has a name. It's called the conservative iconal phase of this scattering process. So if one were able to compute this iconal function, iconal phase, plug it in here, one would find correctly the observables at order g square and through these orders in spin. And I'm saying that one would find to these order correctly is because they have been checked by other means, by directly constructing a Hamiltonian, solving the equations of motion and comparing with this. And the conjecture is that this formula or a formula like this should hold to all orders in the spin and also to all orders in Newton's constant expansion. There are a few remarkable things about this formula. Perhaps the most interesting of them all is that there seems to exist a single function chi, which captures all the complicated dynamics of spinning bodies. As you know, spinning scattering no longer happens in a plane. It's a fully three-dimensional process, which and the various angles depend in non-trivial ways of spin. And nevertheless, there seems to exist a single function that captures all of this and definitely captures it correctly through this order. I should say that there are other amplitudes-based approaches, which I mentioned earlier, which apply both to these and also to radiation type observables, which is what I will spend the next minute or two on. So you might recognize a formula from early on. There used to be another term here, but if one is interested in emission of radiation, then that extra term does not contribute. Anyway, one is supposed to construct these two scattering amplitudes, take the conjugate, the Hermitian conjugate of one, and dress the resulting cross-section-like object with gravitational momenta in the final state and integrate over the phase space. And the claim of Kassa, Maybe, and O'Connell is that this will produce the momentum that's radiated in the final state. And of course, intuitively, it's clear why this should be so. We sum over the gravitons in the final state, and those guys are the things that carry away momentum from an otherwise conservative scattering. So this should be the radiated momentum. And here are results obtained by Hermann, Para-Martinez, Ruf, and Zeng that go to order g square and all the way through the g cube. And of course, this is not the first calculation. Well, this is the first post-Minkowskian calculation of these effects, but post-Newtonian calculations have been carried out before, and there is definitely agreement between these properly expanded in velocity and those results. So in the remaining 2 or 3 minutes, let me say a few words about how these calculations are actually done. So the moral is that what we want is to construct an effective Hamiltonian that does not depend on gravitons anymore, but whose scattering amplitudes are exactly those of GR coupled with whatever particles we want to scatter. So for that, at least in the classical limit. So for that, we need to talk a little bit about the classical limit, which is taken in the sense of the correspondence principle. That is, all the conserved charges are meant to be large. And with this in mind, one can quickly figure out that the momentum of the particles that participate in the scattering should be much larger than the momentum that's being exchanged between these particles. And similarly, that the spin of the particle has to be much larger than 1. This is, of course, in h bar equal to 1 units. Otherwise, the second line as much larger than 1 doesn't make any sense. So putting these observations together and also using the fact that Newtonian potential is definitely classical, one expects the following. One expects that the potential, or the Hamiltonian, has roughly this form. By the way, how much time do I have left?
2 minutes.
Thank you. All right. So the reason I wanted to mention this is to stress the fact that this formula emphasizes the fact that loops contain classical physics. So the reason is that this formula that I'm highlighting here is classical because it was constructed to be classical, and yet it depends on Newton's constants to arbitrary high powers. So again, to extract classical physics is not sufficient in this context to look at just tree-level processes, but one needs to look carefully at loop amplitudes as well. So the way to extract classical physics from loops follows a flowchart, which is this one. One starts with the full theory, which I'm taking here to be GR plus scalar fields, compute amplitudes, and extract the full the amplitude in the full theory, and do the same in an effective theory with an ansatz potential, and then equate the two. And by equating the two, one finds iterative equations for this ansatz potential, which allows us to basically read what it is. So just to emphasize that this is not empty words, here's the one example that I'm actually going to show. And this is this derives, if you wish, the first order in the post-Minkowskian expansion. This one actually does come from a tree-level amplitude, which is here. So now we want a Hamiltonian that looks more or less like this, with a potential that's linear in Newton's constant. So it has only one interaction vertex of this type. This is the amplitude. The amplitude is just C1. So all one has to do is equate C1 with this, and one reads off the coefficient C1. The momentum dependence is buried in this sigma. Q is what becomes the 1 over r, the Newtonian 1 over r potential, and then all the rest are numbers that depend on energy and so on. So having said this, at higher loops, this becomes substantially more complicated. One has to equate loops in the full theory with loops in the effective theory, but that will determine the next order in this one vertex of the Hamiltonian, and so on and so forth. So since my 2 minutes were up 2 minutes ago, let me skip whatever else I wanted to tell you. But please do feel free to ask about them if you desire to hear about some more details. And let me summarize the things that I said and the things that I did not say. So what I hope I managed to convey by just flashing a bunch of results obtained by many people is that amplitudes offer a new and powerful way to study gravitational problems with or without spin. They've pushed the state of the art in spinless potential interactions. They pushed the state of the art for spinning potential interactions. They offer methods to compute radiative observables. They offer a systematic way to study finite size effects. This I did not mention in the least bit, but I would be happy to. And in a more conceptual, from a more conceptual perspective, they expose and provide inspiration to search for hidden structure and hidden simplicity. I did not mention a close connection between amplitudes and classical quantity known as the radial action, which itself is a generating function of observables. Amplitudes provide complete dependence on velocity and so on and so forth. The application of these kinds of methods, amplitude-based methods and particle physics methods in general, to gravitational wave physics are only at their beginning. The stuff that I told you about happened in the last 2 years plus. There are many intermediate and long-term questions that need answering. They are both of conceptual nature and of a technical or computational nature. Perhaps among the conceptual ones, something that's worth mentioning is to establish a closer connection between open orbit and closed orbit observables in the presence of radiation. and therefore remove the stars that appeared on various slides a little bit earlier in the talk. The methods and techniques that are used, which I did not describe, have definitely not been exhausted, and they could definitely, they can be improved further. There is at least one more order in G Newton that's accessible. With a little bit of luck, 2 orders are accessible. In various other contexts, 5 loops and even 6 loops were successfully completed. So we have ways to go there. And last but not least, it's worth emphasizing that these methods are not, while developed for particle physics and now applied to gravitational wave physics, they're not restricted to these 2, but they could have applications to other areas of gravitational physics. So overall, the future looks bright, and expect renewed progress in the future, near and longer term. Thank you very much.
Thank you very much, Radu, for a very nice talk. Other questions? Yes, I see 1 hand, 2 hands raised. Eric Cassandre-Motin.
Yes, can you hear me?
Yes. Thank
you, Radu, for the talk. I'm sorry, so I'm not a theoretical physicist. I'm coming from experiment and observation. So I'm missing a lot of things in your talk, but you did convey a lot of information. So what I'm curious about is more the high-level objective here. I understand those methods are very powerful, but I struggle to understand where they are going to be powerful. Is this something in which we will gain more easily in the accuracy of the gravitational wave waveform, and in particular the phasing? Is this rather that we are going to be able to extend more easily the limited post-Newtonian expansion that we have today? So this I miss. What is the end objective there?
So the end goal is basically to do both of the things that you said, right? So on the one hand, we are hoping that we will be able to provide complete velocity dependence to higher orders in Newton's constant than currently available in post-Newtonian theory. So, the reason to go for higher order, essentially all orders in velocity, is ultimately the plot that's on the screen at the moment. So just the 3rd post-Minkowskian order, g to the 3rd, all orders in velocity, seems in this particular example that was picked in this paper to get closer to numerical GR than effective one-body theory based on 4th post-Newtonian model, right? So of course, the proof is in the pudding. Will it work also? Will it work just as well once we understand all the details at 4th post-Minkowskian order? I don't know. I'm hoping. This other plot is perhaps encouraging, but we definitely appreciate that this is not a complete story, and there is a large chunk that's not under control, and at least not under our control, that is currently missing from this plot. So things could go haywire ultimately. But if you were to wake me up in the middle of the night and ask me why am I doing this, I will bring you back to this plot. Better waveforms, I'm hoping. I do not know much myself about applications to waveforms, but there are efforts to do this also from a scattering amplitude point of view. These methods that I was, were they? These ones, that they compute, if you wish, an inclusive observable. They basically integrate over everything in the final state. They don't tell you much about, say, distributions or waveforms in general, but perhaps there is a way to modify these calculations like this to produce waveforms. And I know that there is that at least O'Connell and Casso are continuing, and maybe as well, they are continuing their work in this direction. But if this were not to work, one can always go back to the Hamiltonian and compute something like a Hamiltonian, which involves the scattering and some gravitons going out, and then solving the equations of motion that way. And that would produce a waveform model, a waveform that would incorporate everything that's known from, say, conservative dynamics to post-Minkowskian conservative dynamics.
I see that Elias also raised his hand.
Yeah, I have a very sort of basic question. This way we construct an effective theory for the two-body problem. But is there a clear-cut cutoff for this type of construction, and what is it?
Right. Well, an effective field theory typically contains the seeds of its own destruction. So the expectation is that this effective theory will fail at around the size in which, around the energy at which the separation of the two bodies becomes of the order of the size of the two bodies, maybe a little bit larger. So at that stage, of course, we expect that new physics comes into play, and you know, black holes or planets cannot be modeled anymore by point particles. Tidal effects are very important. And at that stage, one has several options. One is, sorry, I'm flipping through this. I'm trying to find a slide that actually does some of this. One can attempt to modify point particle theory and include tidal deformations, operators describing the effect the effect of external gravitational fields on the body itself, like stretching and compressing and you know, changes of shapes. And at the point where these kinds of tidal deformations become important, the original point particle description of the effective theory is definitely failing. You know, parametrically, these effects will come in at, I believe, 5th post-Newtonian order, which is why people have, yeah, anyway, so it's the 5th post-Newtonian order. So there is some overlap with various orders in post-Minkowskian theory, of course. But again, all of these can be incorporated, and at some point the effective field theory has to fail altogether, because at least for black holes, we you know, horizon physics must become important. The actual merging of horizons becomes important, and this is definitely not captured by perturbation theory in GR coupled with scalar fields, no matter how many operators you decide to add to it. So
okay, thank you.
Okay, let's thank Radu again.
Thank you.
And I guess I pass the word back to Elias to tell us where we can enjoy our virtual coffee.
So virtual coffee is virtual. So